Thank you, Abhishek and Sanjib, for the invitation, and thank you all for coming. So I'll just okay, so my lectures will be broadly about optimization and various facets of optimization, and many of these are kind of crucial in machine learning. At some points, maybe I'll connect to machine learning and how these things are used within machine learning and so on. But broadly, the course will be about optimization. Okay. So there are various different facets of optimization that I'll cover during the lecture. So roughly, I can say maybe there will be 5 different parts. So one is convex optimization. Is this size visible at the back? Okay. Yeah. So the second one is stochastic optimization. Then we'll talk briefly about non-convex optimization. Then something called minimax optimization. And finally, we'll talk about something called online convex optimization. Okay, so roughly we can think of each lecture as covering one particular part. And today we'll start with convex optimization. And I'll also give references in every lecture or every topic that we go through. So for this one that we'll cover today, so there are 2 references which will be useful. So one is lectures on convex optimization. This is by Yuri Nesterov. And another one is convex optimization, algorithms and complexity. This is by Jérémie Bec. Okay. Okay. So let's begin. So in this lecture, we'll be focusing on convex optimization. But let me first give you what we mean by optimization. So optimization refers to the task of solving, say, the canonical task of solving something like this. We have a function f of x over some variable x, and we want to find an x that minimizes this function. Okay. And iterative methods are those. So okay, so the first question that comes to mind is how do we have access to this function f? So how can we know what function f is? So we need to know the function f in order to be able to minimize it. So there is a notion of black box oracles. Okay, and a 0th order oracle is the following. So the oracle takes x and then it gives us f of x. Okay, so we are able to compute function at any given point. So if I give you x, the oracle gives me f of x. This is called the 0th order oracle. Then we can think of other stronger notions of oracle, like first order oracle, which will take x and then it gives us both the function value as well as the gradient of f at x. Okay, this is the first order oracle. And then we can again think of second order oracle and so on. Okay, x, and then we get f of x, grad f of x, and then grad square f of x. Right? So we can define multiple variants of these oracles, and the 0th order oracle is the least powerful because it only tells us about the function value, and first order oracle gives us more information, which is in terms of like the derivative of f. Then the second order oracle gives us both the derivative and first derivative as well as the second derivative and so on. Okay, and when we have access to these oracles, we usually think of what are called iterative methods. What iterative methods do is that it will have some initial point, some initial estimate of the optimum, say x0. Okay, and then it will use this to, and then it will query the like whichever oracle we have here. So it will query the oracle at, so let's call this oracle O of x0. So if the oracle is 0th order, we only get f of x. If the oracle is first order, then we'll get both f and the gradient and so on. So using this information, we'll refine an estimate x1. Okay, and then using both x0 and x1, we'll query the oracle at, we could query at some other point, right? Which depends on, okay. So this is part of the algorithm. So how do we go from the oracle query to x1? So let me call this A1 of, yeah. So this will look at both x0 and then O of x0, right? And then we'll get an x1. And then again, the oracle can be queried at some combination of x0, x1, and whatever information that it has previously. And then this will give x2. And then using this, we again query the oracle at some other point, either x0, x1, x2, or something, the combination of them and so on. And then we get another estimate x3 and so on. Okay, so these are the algorithmic steps. Where to query the oracle, and when I get the answer from the oracle, how do I update my estimate? Right? These are the two components of the algorithm. And if we look at some of the most popular algorithms, for example, if you think of gradient descent.
So your A1, A2, they're all going to be different? Or?
It could be different. So all of this is part of the algorithm. And in the most general sense, it could be different. But we'll see what these things are for some of the canonical algorithms. Yeah. So let's actually look at something called
just a note. I mean, so everyone, when you ask a question, please, there's a microphone. Yeah, you have to switch it on and ask so that people online can also hear. So you have to press this. Oh, that's okay.
Yeah. So this, so calling this zeroth order oracle twice,
yeah,
is equivalent to calling the first order oracle once. Is it? Like
in one dimension.
In one dimension.
Yeah, but in multiple dimensions, it's right. You'll pay a factor of the dimension to compute all the gradients. So that'll be something I'll just come to in a minute.
Will give you second, right? That's what you mean.
Yeah, so that would be one of the basic algorithms, which is that. So one of the basic zeroth order algorithms will be the following. So you start with x0, okay, and then query randomly. So let me write it as. So start with x0. Okay. Query the oracle. At a random point. In a ball of ball around x0 with some radius. Okay. So around x0 we have a ball, and then query randomly one point, right? And let it be x1. Sorry, let's call it x1 twiddle. Okay.
So your R is prefixed.
R is a prefixed constant here. Yeah. So the algorithm would do the following: x1 is equal to x0 if f of x0 is less than equal to f of x1 twiddle, and this is x1 twiddle if f of x1 twiddle is less than equal to f of x0. Okay. So you query the function value at a randomly chosen point in the ball, and we only move to this new point if the function value actually reduces. So this is something which works in the 0th order setting. Let's now come to some of the more popular algorithms. So the first one is gradient descent. Sure. The algorithm is the following. So start with some x0. And then xt plus 1 is equal to xt minus this is called the step size. Okay. So this works in the first order oracle. So given a point, so we start with an x0. We then ask the oracle to get us the gradient value at x0, right? And then we do xt minus eta times the gradient at x at that particular point. Okay. And this works in the first order oracle. Okay. And one of the most popular algorithms in the second order oracle is what is called Newton's method.
So you tune that eta if needed.
Yeah, we'll tune this if needed, and we'll when we are analyzing this, we'll also see how this should depend on the function properties and so on.
Thank you.
Yeah. So right now I'm just introducing different algorithms and how each of them works in maybe a different oracle model. And then in a minute, I'll also say about the relations between different oracle models and advantages versus disadvantages and so on. Okay. So Newton's method again starts with some x0, and then the update rule is the following. Okay. So Newton's method at every point xt, it queries a second order oracle. So we get both the gradient as well as the Hessian, which is second derivative. And xt plus 1 is said to be xt minus the Hessian inverse times the gradient. Okay. Hessian is a matrix, square matrix, square symmetric matrix. So xt plus 1 is xt minus the Hessian inverse times the gradient.
So is this in one dimension called Newton-Raphson? Is the same thing? More or less. Right?
It's the same thing, yeah.
Same.
Yeah.
Excuse me.
Yeah,
Why does this step size reduces to the inverse of this Hessian matrix?
So we'll again come. So it turns out that if f was a quadratic function, then this is exactly the solution, and you will reach it in one step. But
Okay.
for general functions which are not quadratics, you will again have some step size parameter here, and then there are variants of Newton's method to actually make it work. Yeah.
But like, what does this Hessian matrix gives us? In that, like, how does it tell us that this is the optimum step size?
So what it tells us is that somehow it depends on the curvature of the problem, and Hessian, basically you can think of Hessian as scaling different axes by different amounts, And the Hessian inverse kind of equalizes all the different axes by making it look like an identity Hessian matrix.
Okay, so
Yeah.
it's like if I think about it, it's like it gives me the eigen direction sort of thing where the eigenvalue is minimum or something like that.
It's not about the minimum eigenvalue. It's more that the step size depends on the curvature of the function, and the curvature can be different in different directions. And
yeah, so it tells me about the directions ki like where in which direction the step size is optimum.
in which direction step size should be large, it increases the step size in those directions. In whichever size directions the step size should be small, it decreases the step size in those directions.
Okay.
Again, this is only for quadratic that this works perfectly, but for other cases, you'll again have some other parameter here to make it more stable and so on. Yeah.
Okay.
Okay. So as we can see, like the second order oracle provides us the most amount of information. So we expect that for an algorithm, it's easiest to use this kind of an oracle, right? So let me define another thing, which is that, okay, so we do these iterative algorithms, and finally we say either convergence rate or iteration complexity as the following. Meaning that after t iterations, f of xt minus f of x star is less than or equal to what? So we can think of different functional forms here. So ideally, we want to see that as t goes to infinity, we want this to go to 0, right? And this kind of tells us how it goes to 0. So we can put different functions here. So one is, say, 1 over t, or 1 over log t, or 2 to the minus t, let's say, right? So these are like completely different kinds of convergence rate that we can get. This is like very, very slow convergence, meaning that if t, if you want, okay, so if you want this to be epsilon, right, then the corresponding number of t that you want here is 1 over epsilon. Here it's like 2 to the 1 over epsilon, and here it's like log 1 over epsilon. Okay. So what this means is that if we want an accuracy of epsilon, how many iterations of this algorithm do we need to run in order to find a point which achieves this amount of suboptimality? And if the convergence rate is 1 over t, it means that the number of iterations required is 1 over epsilon. And similarly, if it's 1 over log t, we have actually need exponential in 1 over epsilon number of iterations. And similarly, if the convergence rate is 2 to the minus t, then we only need log 1 over epsilon number of iterations. Okay. As we can see here, each of these algorithms works in these different models. And in the more powerful models, we expect that the algorithms can actually converge faster, because in every iteration, the algorithm is getting more information compared to the previous one, right? However, it turns out that at least in practice, this kind of hits a very sweet spot, in the sense that there is what is known as a cheap gradient principle. Okay, which basically says that if f can be written as a circuit with differentiable nodes. By circuit, all I mean is that we have an input like this. And then we have computation given as a graph or a directed graph, right? And finally, we have an output. Okay, with each of these nodes doing some smooth operation, meaning differentiable operation like addition, multiplication, and so on. Then, if f can be written like this, then gradient at any given point can be computed in the same time as it takes to just compute the function value. Okay.
So this X star, it's you're assuming there's some global minima? Or
yeah, so this is a global minimum. Yeah.
Okay.
So in general, we'll not be able to say things of this sort, right? But for convex optimization, we'll be able to say things of this sort. When we go to general non-convex optimization, we will saying something like this will be NP hard in general. So if you want to focus on tractable algorithms like gradient descent and so on, we'll look for weaker notions of optimality. But this is the like most ideal thing we would want to get.
And so just to be sure, what is convex optimization versus non-convex?
Yeah, so I'll define convex. So I haven't defined convex functions yet. So I'll define convex functions. So far, I guess like I have just been trying to motivate why gradient descent is so widely used compared to other algorithms. And the reason is that is this cheap gradient principle, which basically says that if my function can be written as a sequence of differentiable operations, okay, addition, multiplication, division, where far from zero and so on, right? Then we can compute the gradient of the function f in the same time that it takes to just compute the function value. So in that sense, there is not much difference in the time that takes to implement both the 0th order oracle as well as the first order oracle. And in that sense, we are getting this gradient information for free. Okay. Is one way, is basically how to do this. Yeah.
Shailesh, can you use the microphone again? Maybe you can come here or the back one.
Yeah. So the question was whether backpropagation. Yeah, it was remarked that backpropagation algorithm was is actually one way to actually compute gradient f of x in twice the amount of time that it takes to actually compute the function value for functions that can be written as this as a circuit and so on. Okay. So for that reason, the first order algorithms, in particular like gradient based algorithms, are quite popular because computing gradients does not really take much more time than computing just the function value.
Okay. Excuse me.
Yeah.
Can you explain like with an example?
Yeah. So an example would be if you want, say, x square plus 2x plus 3, right? So the input is x, okay, and there will be one node which is square, right? And then there is another node which is just, let's say, identity or multiplies by 2. Okay, and there is another node which just has a constant 3, and then you have an addition of all of these. Right. So each of these operations within each of these is actually differentiable, right? So this function itself is differentiable, and the point is, in order to compute this, first for x you'll compute x square, and then you'll compute 2x, and then you have 3, and then you add all of them, right? So this takes certain number of operations or amount of time on a computer, and we can compute the derivative of this function also in twice the amount of time, because you compute forward. This is called the forward propagation. And then if you are able to store all these values that you had, then you can do what is called a back propagation. And that will take, so the amount of time taken to compute the function is one forward propagation. The amount of time taken for computing the gradient is one backward propagation, in addition to the forward propagation. Backward propagation is just chain rule. So if you look at the derivative of square, it will just be 2 times x, right? So if you remember what x was here, so you'll just compute 2x, and then here you know that the gradient is always 2, and then right? So this will give you the gradient. So you can think of it as a chain rule of composition. So this thing is composing these functions, and we take a derivative of this with respect to these things, and then pass those derivatives, and then we can take derivative here, and then use the information coming in, and then do the completion like that.
If the function is not polynomial, then it will first approximate it as polynomial.
Actually, not necessary to be polynomial. Even if you have an exponential, for example, here, exp is also differentiable.
Okay. But then the computer, like, it knows how to compute exp directly.
Okay, so this is when you are talking about floating point operations. How you implement floating point operations on a real computer, that will involve quantization and approximating exponential with polynomials and so on. Yeah. But this I'm just saying at an abstract level. If you think of each of these as some floating point operation, which is differentiable and takes, you approximate it as taking unit amount of time, then differentiating through it will also take unit amount of time. That's the, yeah.
So what is a function which cannot be written as a circuit? Like,
so for all practical purposes, we we think of this, yeah. So I mean, the only thing to note here is that this only holds till the first order. It's not true if you want to compute the Hessian. Just even thinking about it. So the size of the gradient is exactly the same as the size of the input, right? But the size of the Hessian is actually square of the number of input dimensions, right? So in general, it is not true. Like, we cannot compute the Hessian of a function using only constant number of function evaluations. Okay, even if it can be written as a circuit. So yeah, so overall, like, the bottom line that I want to emphasize here is that this is the reason that first order methods are quite prominent in practice, and in particular, like, gradient descent is one of the most popular algorithms. And in the remaining part of the lecture, we'll look at gradient descent. What can we say about gradient descent under various for various classes of functions?
So if it's,
Yeah.
so if it's not smooth, you'll replace it by some subgradient or something.
Yeah, so we'll come to subgradients and so on. So let's first try to understand what kind of functions we can really optimize using gradient descent, right? So if you look at the update rule here and see what are the stationary points, what are the fixed points of the gradient descent update rule, it basically is that so the fixed points of GD satisfy that grad f of x is equal to 0, right? Because we are using gradient to make our update, and a point is a fixed point if and only if the gradient there is actually equal to 0, right? So if you want gradient descent to be kind of at least asymptotically optimal, meaning that all fixed points are actually global optima of the function that we wish to consider, then it seems like it has to satisfy the following property, that grad f at any point x equal to 0 implies that x is a global optimum. Okay. This is when gradient descent will converge to the global optimum. And the remaining conditions, so if you want to consider a class of functions f such that if it also contain, so if f1 and f2 are in f, then f1 plus f2 is also in f. So okay, so what I want to say is that I want to understand what is the broadest class of functions for which I can have a theory of global optimization. Okay, so if my function class is non-convex and so on, in general, if I don't put any restrictions on my class of functions, then global minimization is extremely hard without doing basically something like grid search and looking at every point, right? So I'm asking what is the broadest class of functions that I can look at for which global optimization can be done in a tractable manner, or in particular, even gradient descent can actually do global optimization. Okay, and for that, the first condition that I'll require is that the fixed points of gradient descent are indeed global optima, meaning that for any function in this class, if gradient at a point is equal to 0, then x is actually a global optimum. The second condition that I want to assume is that I want my function class to be at least closed under addition. Okay, if f1, f2 are in my function class, then f1 plus f2 is also in my function class. And third, I would like very simple functions like linear functions to be in my function class. So by linear functions, we mean functions of the form So it turns out that this uniquely characterizes a class of functions which are called actually convex functions. So the proposition is the following. So the class of functions f satisfies the three assumptions. One, two, three, if and only if for every x and y, we have that f of y is greater than or equal to f of x So this is the definition of convexity.
So this notation is just a dot x, right? Like
Yeah, this is inner product of
inner product
vector
of
a and the vector x.
x.
Yeah. Okay. So the proposition is that the function class f that satisfy maybe let me yeah. So any function class f that satisfies these assumptions satisfies it if and only for every x and y, and for any f in the function class f, we have that f of y is greater than or equal to the first order Taylor expansion of f taken at x. Okay. And the proof is actually quite simple. Right. So let's say we are given x, y, and then f also, right? Or let's say we are given x and f. We define a new function g over y. Which is this. Okay, so this is a function of y. So the gradient of g with respect to y is nothing but grad f of y minus grad f of x. Okay, so if f satisfies all these three assumptions,
So you're also assuming that all functions are smooth at this point, at least the gradient.
yeah, so I did not want to get into subgradients and so on. So in general, you can replace it with some other vector. So for every x, y, f, for every x and f, there exists a vector which only depends on x,
Okay.
for which this is true for every y. Yeah. Okay, so grad g of y is this, and by the assumption, so if we assume this, so grad g of y equal to 0 implies y is a global, so let's say y star. Y star is a global optimum of G. Okay. So in particular, we know that this is optimized. Okay, right? So we know that if we put y equal to x, this is actually equal to 0. So this implies that g of x is less than or equal to g of y for every y, and g of x is equal to 0 because by definition of this function. Okay. So this basically proves that if f satisfies these three assumptions, then this condition is satisfied, right? And similarly, if we know that this condition is satisfied for the function class f, then we can again easily show that all these three conditions are true. So the reason that we did something like this, again, just to recap, is that we want to look at the broadest class of functions for which we are able to do, we were able to do a theory of global optimization, where global optimization is tractable, and convex functions, in particular functions which satisfy this kind of property, turn out to be natural and somehow like the largest class of functions for which we can do a computationally tractable theory of global optimization. Okay. Yeah.
Does the first assumption imply that there is only one optimum point? Because
no, this is not necessarily true, because there could be gradient could be equal to 0 at multiple points, but it does imply that there are no, any local minima is also a global minimum, right? So there are no local minima. There will be multiple points. The function value at all of them is the same, and all of them are global minima. Yeah. Okay. Okay. So this is basically the definition of convexity. So I'll state it in a bit more generality, which might be useful later, but yeah. So a function f from, say, some set x to R is said to be convex if for every x there exists some vector, let's call it g of x, such that yeah, so let's say this x is contained in some d-dimensional space, then this g is also contained in d-dimensional space, and this is the inner product between these two things. Okay? And for most things, we can think of g of x as basically equal to the gradient of f at x. Okay, so the definition of convexity makes sense. Any questions? We'll just go through some examples to understand what this means.
Excuse me.
Yeah.
What is the difference between the usual definition, which is f of x plus f of y has to be greater than f of
So
y?
that's actually, that can be shown to be equivalent to this. For our purposes, this is actually more useful because we'll be working with gradients and so on, but both the definitions are equivalent. So there is, for differentiable functions, it's very easy to show. For functions that are not differentiable, it's a bit more technically involved because you have to look at directional derivatives and then have to show some directional derivatives exist, and then you can again show this appropriately. Okay, so let's look at some examples of convex functions. So the first one is what is called linear regression. Okay, so A is a matrix, X is a vector, so A times X is a vector, B is again another vector, and we are taking the L2 norm square, which is just the sum of squares of all entries of this vector. Okay, and why is this convex? So if you look at the gradient of this, it turns out to be A transpose times AX minus B. Okay, and if you look at f of y minus f of x minus grad f of x times y minus x. So this is nothing but half okay, and if we expand this carefully, it turns out that this is actually nothing but okay. So there are a few more things that I can maybe just state, and hopefully this can be good for the tutorials to try to show that these things are true. So yeah, so another thing is so f of x, so let's say in one dimension, okay, mod x to the p is convex, okay, and then this also means that f of x is equal to the LP to the P norm. This is for P greater than or equal to 1 is also convex. Okay. So the two things that will be useful for us are composition theorem. So one is so composition theorem basically says that if f is a convex function, then first doing an affine transformation on x and then applying this convex function. If we call that new function to be g of x, this is also convex for any a and b. So a and b are some fixed linear maps, and g of x, which is f of ax plus b, is also a convex function. And the other thing which will be useful to us is the following: if f1 all the way up to some fk are all convex functions, then their maximum is also convex.
The third one, what is the subscript?
Subscript is also p.
So what is that? The
LP to the p norm.
Oh, LP, okay. Okay.
Yeah. So dimension here does not matter. Yeah, it could be, x could be multi-dimensional. So in one dimension, it's the same as this. In multiple dimensions, it's just
one dimension.
1, 2 dimension. Okay, so this basically says that if you have k different functions f1, f2, all the way up to fk, each of which is convex, then their maximum, which is defined to be this function f, which is max over I fi of x, this is also a convex function. Okay. So these things I'm saying because this kind of generalizes, even though we had like a simple convex function to start with, and there are some other prototypical convex functions, we can expand the space of convex functions by using these composition theorems, because we can apply any affine transformation and then apply this convex function. Similarly, if we take maximum over multiple convex functions, that also tends to be a convex function. Yeah. There could be many discontinuities, so it need not be differentiable, and then we'll have to use the more general version there. Yeah. Yeah. Usually no. I think like for these probably again like the measure of the discontinuity points might still be of a lower dimension compared to like measure maybe 0. But in terms of optimization, you are actually trying to find an optimum point. So you do need to be able to handle discontinuities. And it turns out that handling discontinuities follows naturally if you use the more general definition of convexity that we use there. So now that we have done the background, so let's come to the first analysis that we'll do of gradient descent for the space of
am I audible?
Lipschitz convex functions. Yeah.
So in the fifth one, so each f1, f2 up to ft are the individual function, right?
Yeah.
So maximum of fi means a maximum function one from 1 to t. Any one of. So so in beginning we say all are convex. Then in the last we are say the maximum also be convex. So
Yeah, this function
What's
f
the new?
is convex.
And if I also individual also are convex.
Yeah, that's the assumption, and this is the claim.
Initially we are saying all are the convex, then we are saying the maximum also be convex. So the same thing, kind of like.
I
if
mean,
one, yes.
so f is a different function, right? F is again like a single function which is gotten by taking a maximum over these different things. So
Oh.
f will be equal to f1 in some part of the domain. It will be equal to f2 in some other part of the domain, f3 in some other part of the domain, and so on. Right, wherever the max is achieved.
So then this,
Okay.
suppose F1 has a minimum at one point,
Yeah.
F2 has a minimum at another point, a maximum at another point, then this, this is just the upper envelope, right? So it need not have single.
Yeah, so there's actually a maximum, right? So if you have something like this and then something like this,
Okay, but then this.
so the maximum will be this one.
It's just okay.
Oh, okay. Okay. Now it's clear. Yeah. Thanks.
Yeah.
Okay, so let's now come to the first theorem that we want to prove in this lecture. Sorry?
In that example you gave,
This one?
yeah, let's say it doesn't go all the way to infinity, but it's bounded. Then you will have multiple minimums, right?
Bounded
Let's say it goes from -5 to +5.
in the x-axis, or?
Not the x, just the part. Yeah. So let's say the first function goes from -5 to infinity, and the other function goes from -infinity to 5.
I mean, all of them have to be defined in the same domain. Only then, like a max will be meaningful. Yeah. Okay. So the theorem is the following. So if the functions, so if f is convex, so let me first write that. So is the claim clear?
So again, when you're writing, your del again is the
Just a minute. Yeah.
the abstract object there. It doesn't have to be the gradient.
It doesn't have to be the gradient. This has to be the same sub.
Same
Yeah,
abstract.
same thing, same object that we defined. Okay. So what we're saying is the function f is convex, and it is Lipschitz, meaning that the norm of the gradient at any point is bounded by some quantity g. Okay. Then what we are saying is if we do gradient descent, meaning that we update xt to be in this form, xt plus 1 is xt minus step size times the gradient at xt. Then we look at all the t iterates, and then this is the suboptimality of the tth iterate, because we are looking at f of xt minus f of x star. Okay. And then we are taking an average. We are summing over all the iterates equal to 1 to t and then 1 over t. Okay. We are saying that the average suboptimality is upper bounded by a quantity like this. Okay. And why is this useful? So this is the theorem. So if we set eta to be g times norm of x0 minus x star divided by square root t. Okay. Then what we get is that average suboptimality is less than or equal to g norm of x0 minus x star divided by square root. Okay, where t is the number of iterations. Okay. Any question about the result or why this is useful? So what we are saying is that if we do t iterations of gradient descent, we will have seen t different iterates of xt, right? And this measures the suboptimality of the tth iterate, because we are looking at f of xt minus f of x star. So x star is the optimum of the function, global optimum of the function. And then we are taking average over all the t iterates. So what we are saying is the average suboptimality is bounded by this right-hand side. And for the right-hand side, we have the step size parameter, which we have not set, which is a parameter in the algorithm. If we set that parameter to be g, so g, which is the bound on the gradient, and then norm of x0 minus x star, which is the distance from the initial point to the optimum point, divided by square root t, then what we get is that we can, so this one, we can just substitute this eta here, and then it simplifies to this quantity, which goes to 0 as t goes to infinity.
So you're just matching the two things.
Yeah, I'm just matching the two things. We can choose the best eta that minimizes this. Okay.
Yeah, that should be, I think, 1 over g.
Sorry?
That should be 1 over g, I think. X naught minus x star by g.
Sorry, where?
In that expression, eta equal to, if we set, yeah, that should be 1 over g, I think. G should be in the denominator.
Ah, okay, right. Sorry. Thanks. Yeah. Yeah, thanks for the catch. Yeah.
Does the theorem imply that the scale of time scale is 1 over t or 1 over t to the power?
Yeah, so this basically implies that this is actually 1 over square root.
You think for Newton-Raphson method, it's always 1 over. If eta is used in such way?
No, so this is for gradient descent, right? And also we are making this assumption that the function is Lipschitz. We are not making any further assumption about the function. So we'll see that we can make different kinds of regularity assumptions about the function. Here we only assume that the first derivative is bounded. We can assume that maybe second derivative is bounded, we'll get a different thing. If you assume third derivative is bounded, again, we'll get a different thing and so on. So the more regularity assumptions that you impose, you can actually keep on improving this. And hopefully today we'll also see that this is kind of the best possible in the first order oracle model, meaning that information theoretically, you cannot do, like there is no other algorithm which can get a better rate. It's not just about gradient descent, but you can use any other algorithm, for example, and this is still the best rate that's possible to be achieved. Yeah. So hopefully, like at least the result and why it's useful is clear. Yeah.
So the way that fixed is by demanding that the left that the combination should.
So we'll just minimize this over eta. So this is a function. If you think of this as a function of eta, where eta is a parameter of the algorithm, which we have choice to choose. We just minimize this function as over eta. Yeah, and then if you set gradient equal to 0, we'll just get this. Yeah. Okay, so let's look at the proof. The proof is again quite simple. So we know that xt plus 1 is xt minus eta times grad f of xt, right? So if we look at the distance to the optimum, xt plus 1 minus x star, the square of this. So we can plug in this quantity for xt plus 1 and then expand the square. So we get something like this. Okay. And we now use like both the assumptions that we had. So I have put a less than or equal to here. So the first term I'll just use as is. The second term, by the convexity assumption, we can show that this is actually greater than, this gradient part itself is greater than or equal to, and so this is less than or equal to. Okay, so this is because of convexity. And then because the gradients are bounded by the Lipschitz assumption. Okay. So I have used convexity here in order to upper bound this quantity, and then the Lipschitz assumption here to upper bound this quantity. And if we rearrange, so what we will get is so just rearranging this gives us this, and then so we just sum over T and average. Okay, so if we take a sum over T and average, there is a telescopic sum here. So only the first and the very last terms remain, right? And that will give us this first term. And then like we'll just throw away this negative quantity. That will give us this term. And then this one will be exactly the same. So this is 2. So a couple of remarks. So the first remark is that we can see that the only things that the bound depends on is the norm on the gradient. and then the distance to the optimum, and then number of iterations. So there is nothing about the dimension of the problem. So the X could be actually in a very high dimensional space. But even then, in terms of the convergence rate, we actually don't see the we see that there is no dependence on the underlying dimension. And this is particularly important for very large scale dimensional problems, where the dimension may be very, very large, and still we want to be able to get to the solution much faster without much depends on the underlying dimension here, right? And gradient descent precisely has this sort of advantage. And the second one is that in order to set this optimal step size parameter that we have here, we needed the knowledge of this bound on the gradient, and we needed bound on the distance to the optimum, right? And there is actually a lot of work on designing parameter-free algorithms, which actually don't need to know or estimate like either of these two things, or even if they're estimating, estimate in a much like very, very efficient manner, but will not go into those things at least as part of this lecture. Okay. And the final thing that I want to say here is that all we needed was, we don't really needed this thing to be the gradient, as was pointed out earlier, but rather any vector that can be computed at xt is sufficient. Okay. And in general, that's the notion of subgradient. And this is one way to define a subgradient for a convex function. Yeah.
So there is one more term, right? Usually from the other side when you do this telescopic sum. So you are assuming that at the end you have reached the optimum?
No. So that has a negative in front of it. So you can just throw it away.
Okay.
Yeah. So it will be x0 minus x star minus something. So I just threw it away. So a vector w or vector g of x is so let me write this. So g of x is subgradient of a convex function f at x if the following condition is satisfied: f of y is greater than or equal to f of x for every y. Okay. So in convex function, for simplicity, I defined this to be the gradient of f. And if the function is differentiable, that's the only thing that actually makes sense here. Okay. But there could be non-differentiable functions for which this still makes sense. So a simple example is the following. F of x equal to mod x. Okay. And for this, subgradients are defined as follows. Okay. So for function f, which is equal to mod x, the absolute value of x, the subgradient of this function f at x is given by the set of subgradients is given by the sign of x if x is not equal to 0, and it's the entire interval from -1 to 1 if x is equal to 0. Okay. So I guess like the kind of equations that are implied by this is the following: mod y, which is f of y, is greater than or equal to mod x, which is the function value at x,
Sorry, Praneeth,
Yeah.
so, the subgradient at x equal to 0, what is that? -1 to 1? I mean,
This is the interval from -1 to 1. So we are saying the set of subgradients. So if a vector G is said to be a subgradient if it satisfies this. Given an X, there could be multiple G which satisfies this equation. And we are saying like the set of all of that is given. So we can take any element between -1 and 1 that will satisfy this condition. So that's what I mean here. Okay. So what this means is that we look at the function value f at any point y, which is equal to mod y, right? It can be shown that this is greater than or equal to mod x plus sine of x times y minus x if x is not equal to 0. And this is greater than or equal to mod x plus alpha times y minus x if x is equal to 0 for any alpha between -1 and 1. Okay. And so if x is equal to 0, this is actually just equal to alpha y, right? And if alpha is between -1 and 1, then mod y is always greater than or equal to alpha y for any alpha between -1 and 1. Okay, so why did we go into subgradients and so on? The reason is that if we only assume a bound on the Lipschitz parameter, it turned out that for gradient descent, we got this kind of convergence rate. And a natural question that we ask from a computational point of view, anytime we have this kind of convergence rate is this the best we can do? Can we, for example, get something like 1 over t? So 1 over t goes to 0 faster than 1 over square root t, right? So can we design an algorithm which can actually get a convergence rate of 1 over t, right? So that's the kind of question that we ask. And it turns out that we cannot do better than 1 over square root t in this only under these assumptions. And we'll now construct a example where there is no algorithm which can do better than this 1 over square root t convergence rate. And yeah.
But I can choose eta in such a way that it goes faster than 1 by square root t, no?
No, we cannot choose any eta because like there is a trade-off here, right?
Sorry? They have two terms, right? There's a competition between the two.
Oh, okay.
Okay. So to optimize.
So this eta indeed minimizes this entire quantity. So any choice of eta will not help, but you can think maybe could I have done like a different update rule? So why this update rule? I could have done some other update rule, right? And these lower bounds are there to tell us that there is nothing else that we could have done to get anything better. And this is somehow the fundamental limit of this problem. Okay. So the full information theoretic lower bound is a bit more complicated, but so we will just work in the span of so for a special class of algorithms which still captures gradient descent and like pretty much all the algorithms that we have been able to think of in this first order oracle model, and that is called the span following algorithms. So the algorithm is the following. So at any, so fix x0. Okay. Xt can be any point which is in the span of, span meaning like linear span of these vectors x0, grad f of x0, up to xt minus 1. Is the model of the algorithm clear? So we initially start with x0 and we can only query the gradient at that point x0, right? And then we'll have x0 and grad f of x0. We can pick any point x1 which is in the span, linear span of x0 and grad f of x0. Okay, that's kind of telling us that we could have chosen any step size at least in the first step, right? And also the quotient in front of xt need not be 1. It could have been anything else, right? And then we'll get some vector x1, right? And then we ask the gradient oracle at that point x1, and then we get the gradient at that point. And then the second point can be in the span of x0, grad f of x0, and grad f of x1. this is kind of a very fairly wide, like fairly rich number of update rules that this captures. And we want to show that any algorithm which is of this form cannot get a better convergence rate than 1 over square root t under the settings that we just discussed here. Okay. Okay. And so the first one is like a model for the algorithm that we have here. So again, I want to reiterate that we are not making this assumption, like this assumption is not fundamental. It helps us come up with like an easier proof, but there are information theoretic arguments which can argue about any algorithm, including randomized algorithms and so on. Okay. But the main intuition is again the same construction that we are going to do now, but this and we can think of our proof will be for a particular specific class of algorithms which follow this particular paradigm. But the argument can be generalized, in particular, like the lower bound instance can still be extended to any arbitrary, even randomized algorithms under this black box oracle models. Okay. So the second one we need is a class of functions f. Okay. And this will be parameterized by G, R, and the number of iterations T. Okay. So given a bound on the gradient and a particular radius R, meaning that and then number of iterations T. So we'll construct a class of functions of the following form. Okay. Some class of functions.
So I mean radius search only in the radius of.
Yeah. So we will be guaranteed that the optimum is actually within this ball of this radius. So you don't even have to look outside that ball. Yeah. So the functions that we'll define will be of the following form. Okay. So we'll be defining a function in RD. So we are given some particular GRT. Okay. And the kind of result that we want to say is that you pick any algorithm in this class. Okay. And let's say it finally outputs some point xt after only t iterations. Then its suboptimality is lower bounded by something of this quantity. Okay. Okay.
Sorry.
Yeah.
What is, can you say again, what is R?
Yeah. So R, okay. So here if we think, so this is kind of R. So when I'm saying a lower bound, so there are 3 different parameters in this upper bound, right? I want to say that none of them can be improved. And this is the best you can get. So what will happen? So in order to construct a lower bound, the paradigm is the following. So you can give me any arbitrary choice of G, R, and T. Okay? And then I'll give you a problem that I construct. And then I'll be able to show that it doesn't matter any algorithm that you use. After T steps, it's like the value of the point that this algorithm gives on the function that I constructed is no better than this quantity.
So now the algorithm has freedom in choosing this how the span is defined.
Yeah, exactly. So span in particular has these coefficients that you put on each of the things.
Okay, so those
the
will
algorithm
vary
can
and-
choose those things whichever way it wants.
Okay.
And still I'm saying that, yeah, I'll write on the theorem, but basically whichever way you give for this particular function,
Okay.
the algorithm cannot output a point xt, which is better than this quantity.
But now you're choosing some specific function, is it?
Yeah, actually I'm treating a specific function. So you need to go to maybe a general function class if you are looking at randomized algorithms and so on. But for now, like, let's just look at a specific function. The thing is, like, if you want to do for general algorithms, you cannot give like a single function, because the algorithm can just memorize what its global minimum on that particular function is and just always give you the same answer, right? So when we go to more general algorithms, we will need to have a function class, but for now, let's just stick to this particular function. Yeah.
So this function you are generating by the points you got it from that algorithm?
No, no, no. So these are two different things. So one is I'm saying I'll only consider these kind of algorithms, and these kind of algorithms cannot do very well. Okay. And in order to prove that it cannot do very well, I have to construct a function on which it will not do very well. And that function is this.
So if you take this t iteration,
yeah,
basically, then you have all these xi's.
Yeah. And so for different choices of algorithms, you will have different choices of these xi's, right?
Yes.
You take any of those algorithms and any of those xi's.
Yes.
Then the suboptimality is lower bounded by this quantity.
So suppose you wanted to optimize some function which was f0 of x.
Yeah.
Right. Which you use one of these algorithm which generates this x1, x2, xt1.
Yeah.
And then you have this function f of x, which need not be the.
No, this is the function that I'm trying to optimize.
This is the function you're trying to optimize.
So, okay, so let me maybe write what I want to exactly say.
But this xi's, how do you know this?
Xi's are iterates from this algorithm, is it?
Oh, sorry. Yeah, so maybe, so let me call this something different. So let me call this superscript.
Okay. So this has nothing to do with the top.
No, this does not have anything to do with the top.
So now this xi, how are you getting this xi?
Yeah, so that's a good point. So x is a vector. X is a vector of d different coordinates. And I'm saying if I give you my vector, the function f is defined in this particular way. You take max over like the first some number of coordinates and then multiply gamma plus mu over t times the sum square of all of these. So that's this. So that's my function f. Okay. And then I'm running an algorithm. So let's say I run gradient descent on this problem, right? It will generate a sequence of x1, x2, and so on. So the theorem is that, so let A be any algorithm satisfying this condition. Okay. So A generates iterates, after T calls to the oracle, the first order oracle.
So what is this gamma?
Yeah, I'll tell you what gamma and mu are. They are parameters.
You'll choose it.
I'll choose the parameters. Yeah.
Oh. That's notice. This is just the sum of x, y, x, I, z.
lower part of the
So-
board is not visible.
Yeah, so let me write this part clearly here.
Algorithm.
xt minus comma. Okay, the gradient is done. Choose xt to be in the span. Xt has to be chosen from the span of those. That's why.
Yeah.
Is this visible?
Yes, it is visible.
Okay, hopefully this is right. So what we are saying is we consider this function for any algorithm which satisfies the span following condition, and in particular, like gradient descent does follow this condition, right?
R is the distance. R is the distance between x naught and
That's correct. Yeah,
x naught and x star.
yeah. So yeah, so I guess like the guarantee here is that again, like we'll choose gamma and mu appropriately so that this is true. So x star is in a ball of radius r. So even if you start at 0, the distance between 0 and then the optimum is at most r.
Okay.
And we have this condition.
So this is for this special function, right? But you're not guaranteed for any convex function that this is still.
So usually the way we want to say about algorithms is that for any function, this algorithm will get this kind of convergence rate, right? What we are saying is that you cannot get such a result for this algorithm.
Okay.
Right? Then maybe you have to use more things about the function. So you have to specialize the function a bit more. And one way to specialize this would be to first observe that this function actually is not differentiable everywhere, right? So if it's differentiable everywhere and then the gradients are actually Lipschitz continuous, can we do better? And then we'll then have to restrict the function classes to exclude these kind of functions. Maybe we can design faster algorithm for that class. Yeah.
Clearly for quadratic, you will do much better.
Yeah. Yeah. Okay. So actually we are, so maybe can I take 10 minutes?
Yeah. Okay.
Okay. So let's do the proof of this.
Praneeth, there's a question in the chat.
Yeah.
Can you please give an example which starts from x0 and we can get other points xi from it by using the oracle that is through iterative method?
I think gradient descent is one example.
Yeah, that is an example.
Okay, so first let's pick the choice of gamma and r. So gamma is chosen to be gamma and mu. So what we are given is parameters g and r, right? We want to construct a function f, which we constructed. We want to show that f is g Lipschitz, then it will satisfy this assumption. Then norm of x0 minus x star is at most r, right? These are the two things that we need to satisfy so that that function actually satisfies the hypotheses in this theorem, right? And then we want to say that this is the best possible result that we could have gotten using any other algorithm. Okay. And for that, we are choosing gamma and mu in this particular way. Okay. So first, let's compute. So let me first say the following, that so the claim is that x star is given by the following. So if you look at the ith coordinate of x star, okay. So the claim is that this is the optimum of this function. Okay. And what we need to show is that, okay, so once we show this, we need to show that the norm of this function is less than or equal to r, so that this being less than or equal to r is satisfied, right? Then we have to show that this function is g Lipschitz, as is assumed in this theorem. And then we want to show that if we use any algorithm of that sort, after t iterations, we'll still not be able to find a point whose suboptimality is less than like this quantity again. Okay, so let's first show that x star is optimal, and for this we need to understand what is the subgradient of the function f. Okay, so the subgradient of f. So we'll use gradient. So this notation to also denote subgradients. So this is given to be, or like let's use this one. So convex hull of all the EIs such that I is in I of x. EI is a standard basis vector in the ith coordinate. And so the subgradient of f at any point x, as we said, it could be a set. It need not be a single vector. It will be a single vector if the function is differentiable. If the function is not differentiable, it can actually be a set. It's given by mu x plus gamma times the convex hull of all the EIs. Okay, where I is in I of x. So EI is the standard basis vector in the ith coordinate. Okay, and I of x is the set of all j, all the coordinates j, for which xj achieves the maximum value of xi. Okay. And convex hull basically means that summation alpha I ei such that summation alpha I is equal to 1. Okay. So whatever vectors are there in ei, Okay. So firstly, the gradient, subgradient here, right? So if you look at the norm of any subgradient here, this is equal to the norm of mu times x plus gamma times the convex. Let's use summation. And this is less than or equal to mu times norm of x plus gamma. Okay, because A is our unit norm and alpha is sum to 1. So this we can get using just triangle inequality. And okay, so what is norm of x? So we can just restrict ourselves to within the norm of x star. So norm of x star is t plus 1, right? So we can just plug in the values of gamma and mu to argue that this is actually less than or equal to r square. Okay, and if you plug this back in here, so the norm of any subgradient is less than or equal to mu r plus gamma, and we can again substitute things here, and then this is less than or equal to g. So the point is we have chosen these functions, and then we have shown that we know what exactly the optimum is, right? So x star puts a negative amount of mass on all the first t plus 1 coordinates. Okay, and we use the subgradients definition here to argue that this is indeed the optimum. Okay. And then we also use the subgradient definition and the parameters here to show that the norm of x star, the distance from 0 is at most r. Okay, and then the norm of subgradients is always bounded by g. So the point, so now this satisfies precisely the conditions of this theorem, and all it requires for us to show is that the suboptimality of any point that's output by the span following things, which look only for t iterations, is at least this much. Okay, and the reason for that is following. So if the algorithm starts at, so we assume that x0 equal to 0. Again, like if x0 is different, because like it's something that the algorithm is doing without even looking at the function, right? So if x0 is 0, after t iterations, would have discovered only the first t coordinates. So let's again write the function here just for a second. Okay, so this is the function that we are considering, and we have this rule for giving subgradients. Okay, so at x equal to 0, we see that all of them are set to 0, so the max is achieved by all of them. Okay, and the subgradient can just reveal anything in the convex hull of all the basis vectors. So it can just reveal like the first basis vector. Okay, and then the algorithm will only know that the first basis vector or first coordinate is important, and then it can set it to anything which is like 0 or negative or positive. In any case, what you can argue is that the subgradient, so the max in the next iteration will be achieved either in the second or all of the other coordinates. Okay, and then the subgradient in the second time will again be in the span of the first two different coordinates. Okay, and what this means is that every iteration the algorithm knows only one new coordinate at a time, and after t iterations it will only know maybe the first t coordinates, okay, at best. So that in particular, like the t plus 1 coordinate will still be set to 0, meaning that f at x, the tth iteration, is still equal to is greater than or equal to 0. Okay. So the reason for that is that so we have this function. If only the first t coordinates can be set to negative and the t plus 1 coordinate is still positive, it means that this maximum has to be greater than or equal to 0, and then we have an additional term here, right? So the best value that this can take is actually only equal to 0. Okay, and at the same time, if we compute f of x star, where x star is given here, so f of x star is equal to what? So we have this quantity, right? So gamma times the maximum is minus gamma over mu times t plus 1 plus mu over 2 times the norm of that is equal to norm square is t plus 1 times okay, this is nothing but minus gamma square to mu t plus 1. Okay, and if you plug the values of gamma and mu here, so gamma square is t plus 1. And 1 over mu is so f of xt is at least positive, and f of x star is actually equal to this. So the suboptimality of any point that's output is at least this much. Okay, so let me stop here. Happy to answer any questions.
So if you take this d equal to 2, this one, right? I can take d equal to 2 also, right?
T?
D.
So d has to be greater than or equal to t plus 1.
That was my question also. So do you think if you have small dimension, you can do better?
Yeah, yes. So there are algorithms like cutting plane methods and interior point methods and so on, which are much more sophisticated. So here, as I mentioned, right, so the convergence rate was independent of dimension. We only had dependence. So for example, here, like here, this was the convergence rate also we got. There was no dependence on the ambient dimension. So these are called dimension-free methods for convex optimization. So in there, these are lower bounds, and in particular, like these are tight when the dimension is very large. If the dimension is smaller, you can do much better, but the convergence rates will depend on the dimension. Yeah.
So this is not valid for d equal to 2 and capital T equal to 1.
No, this is valid for any t and d as long as this is satisfied.
But then,
the point is that for a large T, you have to choose a big enough dimension.
Yeah, that's correct. That's correct. Yeah.
But suppose I first choose D.
Yeah.
Like I said, D, I choose to be 2.
Yeah.
And I just do one iteration.
Yeah. For within one iteration, you cannot really converge to optimum. You need at least 2 iterations. And at that point, the number of iterations becomes comparable to the dimension of the problem. Okay. And there are these cutting plane methods. So in terms of oracle complexity, there are these center of gravity method and so on, which tell you that so F is convex, okay, and G Lipschitz meaning the norm of the gradient is bounded by G. And in a ball of radius R, okay. So center of gravity method requires these many queries to the gradient, D log to output an epsilon optimal solution. Okay, so here the number of iterations is actually log of 1 over epsilon, right? So this one is also a bound. This one is also an upper bound. The other one is also an upper bound. But the thing is, in the example that we constructed, D is actually much larger, right? D is greater than or equal to T. So this is gotten by And the other thing is, here I'm only talking about the number of queries to the oracle. I have not told you what kind of computation that will be done in each iteration by the algorithm after it gets the query. Here actually like the, each iteration is actually very complicated, meaning that you will have some set that's defined to you, and then you have to find some center of gravity of that polytope, and then you query the function oracle at that particular point. Right, and then that will give you one more constraint. You add that constraint to your set, and then you again find the center of gravity and so on. So these methods for small dimension optimize for the number of gradient oracles, but in terms of computation, when you combine both, what amount of, so this is still an abstraction, right? Usually the function is also there is some amount of time that you want to spend in computing the gradient of the function, and then there is some amount of time that you want to spend in using that information to update your estimate. So here it's completely optimizing the amount of time it takes to the number of queries it makes to the oracle, but the computation that's required per step is extremely large. And even in smaller dimension, there are other still sophisticated methods, but still requiring something which only logarithmic in GR or epsilon, but something polynomial in the number of queries. Yeah.
So just one question. There are also gradient methods which kind of approximate the second order by squaring the gradient or computing.
Yeah, that's correct.
Elements of the Hessian. Does that lead to improved convergence?
In some cases, for very special cases, people have shown that they can be probably shown to improve the convergence rates. But in general, there's a broad theory of adaptive optimization, or I would say like the practical success is still far more surprising compared to whatever we know about them in theory.
Okay, I think maybe we should stop because to break for lunch and then the next lecture.
Sure.
So I think Praneeth, you said you won't be there for the tutorial, right? So
yeah, tutorial I will not be there. So I think some of the problems that I mentioned in the beginning, like some of the examples of convexity, and another easy thing would be, so we did the proof of gradient descent. If gradient is not available to us exactly, but is available to us only with some additive noise. We can again get a understand like what's the best convergence guarantee we can get. And gradients are not exactly computable. I can share over email like a more precise statement.
And if there are any questions, people can ask tomorrow morning, like before the lecture.
I'll be here much before the lecture.
Okay.